Welcome to another Octagon Silo Math worksheet. So this one works a little bit differently, has a few extra questions here, and it has a little bit of a different way of figuring out the math. That way you have a couple of options or alternatives should you forget one or the other, or depending how your instructor does the math, so you can follow along. Let's have a look first at what we're trying to figure out and what we even see here. So we have another silo where there's an octagon shape on the outside and there is a circular silo on the inside. The silo would get filled within the circular portion, and everything that you see here is going to be concrete. And then we also have a footing around the outside and the dashed lines, also in octagon shape. So let's look at some of the the numbers. The octagon outside to outside from our wall shape is 5,900. Then we have a section AA at the thinnest part of the wall, where we can see that the footing is 300 mils thick. The footing extends by 200 mils past the wall. The walls themselves are 2,600 tall, and the walls are 250 mils thick. So everything here is in millimeters. We're going to be working with area, so square meters, cubic meters, and we're going to be working with some weights and forces and pressure as well. Let's have a look at the questions. We're figuring out volumes of walls in cubic meters, of the footing in cubic meters, the capacity of the tank when completely full in cubic meters, so that's the inside. Then working with just figuring out the density of the concrete portions, so of the walls and the footings, what the bearing capacity of the soil would have to be like in kilopascals. Then what if we filled the tank full of water? How many kilopascals of pressure would we need to be able to, or would the soil need to be able to support? Then what if we filled the tank full of steel? So 3 times after another. It's kind of the same thing. You're just popping in different numbers. And then at the end, if we put the tank and the footing structure in some water, so giant bathtub, by keeping the inside of the silo empty, would it float? So it's actually a really interesting worksheet. Granted, for carpenters, probably more than what we need to know, but it'll be great exercise in math anyways. So before we get started with the actual numbers here, I want to show you a little bit of basic octagon math first. And I'm going to be writing everything out so you can write along with and see how I take notes to then have it make sense later. So basic octagon math, when the sides are all the same, we can actually draw a square around them. Right? You can see that this is an octagon shape and that this is an octagon shape here. So if I were to draw in these lines to create that square, this is what we would get. Oopsie. That one went a little wild. There you go. So that's the idea of an octagon, that we can fit an octagon inside of a square. Now, to find out the length of a side for an octagon, the way I want to show you in this video is I want to turn all the sides into a 1. So I'm just going to say that each side of the octagon, and they're all the same, right, equals just the number 1. And we want to find out first what the full length across is, if I may say that, in ratio and proportionally compared to our 1. And I want to find out what these triangle numbers are here. So perhaps you remember Pythagorean, right? We have 90-degree triangles. A squared plus b squared equals c squared. So I want to show you the ratio and proportion of this. So we're going to say that C is 1. That's what we're saying. And we want to find out what A and B are. And because it's a 45-degree triangle, because that is the whole idea of an octagon, both A and B are going to be the same. So instead of a plus b squared, we could also say it's a squared plus a squared equals c squared. Regular old math, 2a means 2a squared equals c squared. And now instead of continuing with c squared, we can just use the 1 because we already have a number for that. So 2a squared equals 1 squared. Now, so if we divide this in 2, what we have to do on one side, we have to do on the other side. So 2 divided by 2 leaves us with a squared, and 1 divided by 2 leaves us with 0.5. And we still have the squared over here. So now if we want to get rid of that square, we have to take the square root. Well, square root of a squared is a, and here we end up with the square root of 0.5. Now, if we actually punch that into the calculator, let's pop that in here. Square root 0.5 gets us 0.707. So what does that mean? Well, it means that this right here is 0.707. This is 0.707. This is 0.707. And this is 1. Now, can we figure out in the way that we're doing ratio and proportion what the total distance would be across? For the square or for the total length across for our octagon? Well, we just punch it into the calculator, right? We have 0.707 over here, we're calling this a 1, and 0.707 over there. So 0.707 plus 1 plus 707 gets us 2.414. So what that means is that the side of an octagon is always 2.414 times smaller than the distance across. And that's a really important number that we're going to have to remember for later. But that makes it really easy to find out the length of the side of an octagon if all we have is the number across. Like in this example, we have the 5,900, right? We don't actually have the length of any of those sides, so we have to figure that out first. So this is one way of doing it. And I only showed you this to show you where that 0.707 or square root of 0.5 comes from. I find it easier to understand when you see where things come from. Important to note though, if all you can remember is that the length square across is 2.414 times bigger than each side of the octagon, then you'll be doing great. So this is one way that we can figure it out, or we could also do some SOHCAHTOA. So let's draw this out as a triangle. We're still calling our side 1, so that's it. And I always draw myself out the SOHCAHTOA triangles. I already know that we're going to be using SO. But let's see here. So we have an angle and we have a hypotenuse of 1, and we want to find out the opposite side here. So if I mark out the O, what we have left is S times H, which means sine of 45 degrees times the hypotenuse of 1. And if this is confusing to you, just watch my trigonometry videos and you'll easily understand. Sine 45 times 1 also gets us the 0.707. So there are a couple of ways that you can figure this out. And then you can still add them together to get that 2.414 situation figured out. So important here is that we figured out the 2.414. That is most important. Okie dokie, maybe now we can actually start with our mathing. So what's the first thing we want to figure out? The volume of the walls in cubic meters. It is so important to keep proper track of what you're doing. It is so easy to lose track. Um, yeah. So first, we want to find the overall area of our squared off octagon, right? I kind of continued the lines here, and that's kind of easy to find out because we already know the number across. So overall area of the octagon. Well, 5,900. So we're going to, anytime it's meters and cubic meters or area and volume, we want to turn it into meters. So 5.9 meters times 5.9 meters. 5.9 times 5.9 gets us 34.81 square meters. Now, that is the entire square. Obviously, we have a few triangles here that we still need to deal with, and we get there in just a second. Now we need to find out what the actual side of the octagon is. While we found out that the side is 2.414 times smaller than the distance across, we haven't actually done the math yet. So a distance across is 5.9 meters. And now we divide it by that 2.414 of our ratio and proportion. That's all that it is. So 5.9 divided by 2.414 gets us 2.444 meters. That is the side of the length of each side, 2.444. Right? That's this side, this side, this side, this side, all of them. They're all the same, 2.444. Important to note. Now, we want to find the area not included in the square. Right? So we have the area of the square all the way around. Now we want to find out those triangles. And again, there are two ways of doing this. I'm going to show you both. Let's give these numbers. Now you can use a different color. Oopsie. We've got 1, 2, 3, and 4. Can you see that we have 4 triangles here? So we're going to use that. Also, what we know is that the hypotenuse of these triangles is 2.444, right? That is literally what we just figured out. Now, check this out. We can draw ourselves a square. And we can turn it into 4 triangles. And we can mark them and give them numbers. 1, 2, 3, 4. Right? We have 1, 2, 3, 4. 1, 2, 3, 4. Now, what's on the outside? What's this distance? And what's this distance? That's the hypotenuse, isn't it? That is the hypotenuse of this triangle. That's what's on the outside. And it's the hypotenuse right here, which is the length of our octagon side. So 2.444 across, 2.444. Do you see that? So let's say triangle number 1, if you flip it, right, the pointy bit of the triangle, if you flip it upside down, you're going to get the shape right here. We're not changing the shape, we're just flipping it in our head. So that way we can have the hypotenuse on the outside, and we already know the length of those numbers, right? Because it's the length of our octagon side. So this is actually a really neat way of finding it easily. If you can do that flip in your mind, to use these four triangles and squishing them together in a square. Okay, so I hope that that makes a little bit of sense and we can move forward from here. So the area not included, well, this is just a square. So 2.444 meters times 2.444 meters. Should get us to 5.973 meters squared. That's the area not included. And that is the first variant. And I'm going to show you the second way. If you like trig, you'll like this one. Okay, I'm going to draw myself another triangle. So this is not an extra step, it's just an alternative. If you don't like this, see if you like this. Okay, so we know that this is 45 degrees. And again, the hypotenuse is the length of our side, so 2.444. And if I would like to figure out the opposite again, and I know I didn't quite draw this equally, but both of these sides are the same, right? Because it's a 45-degree triangle. Drawing my SO again. And I want to find out the opposite. So O opposite equals S times hypotenuse. Gets us the sine of 45 degrees times, and now we're, instead of the one from before where we're ratio and proportioning, actually putting in the length of our side, 4, and punching that into the calculator. Sine 45 times 2.444. It's 1.728. So that is the length of one side. So right here, 1.728. 1.728. Right, that's the length of the triangles here. So now, can we find out the area of a triangle? Well, of course we can. We can figure out the area of one triangle. And you can see that we have 4 available to us. So we're going to figure out the area of one, then multiply by 4, which gives us the area for all of it. Area for a triangle is base times height divided by 2, because we could just continue these lines across, right? And now we end up with a rectangle, but the triangle is only half of it, so we divide by 2. Punching in those numbers, 1.728 meters times 1.728 meters, dividing by 2, 1.728 times 1.728 divided by 2. It says 1.493 square meters. So that is the area of one triangle. So area of all triangles, because we want to take off the area for all four triangles, right? Because we're still looking for the volume, and currently we're still looking for the area. So we have our 1.493 meters squared times 4, because we have 4 triangles, times 4 gets us 5.972. Well, 5.972, 5.973, I'm going to say that that is fairly deadly, and you can easily continue with either one and come out with good answers for your problem. So whichever one you feel most charming, that works for you, that your brain can wrap itself around, or really whichever one you're going to remember in a quiz. Great, so now we have the area. Now let's find out the overall octagon area, because we have found out the area of the big square right here. So we're going to go big square minus triangles. And that's the area for both. So 34.81 square meters minus, and we're just going to continue with this one, 5.973 meters squared. How many does that get us? 28.837. There we go. And of course, it's meters squared. And we want to remember that one because next we are going off to do our volume calculation. I'll leave this to the side here so we can look at it again in a minute to find the area. Okay, so now what do we have figured out? Well, we figured out the area of the big square. We figured out and minus the area of the triangles. So now we have the actual area of the octagon, but we just want to figure out the walls, right? So just the walls is all of this. Can you see that? Yeah. All of this. So before we can multiply it by our height to find the volume, we need to figure out the circle situation first. So the area of the circle, okie dokie. So what do we have here? We have the distance of the square across. Now, can we find out what the diameter of the circle could be and the radius? Because the area of a circle, if you remember, is A equals pi r squared. So we need to find out the radius of the situation. Well, the square across is 5,900, right? Now, to find the diameter of the circle, we have to subtract two wall thicknesses, right? We know what the wall thickness is, 250, and it's on either side, so we have to subtract it twice. So diameter circle is the square minus 2 times the wall thickness. Now popping in some numbers, 5,900 minus 2 times the 250. And what does that get us? 5,900 minus 2 times 250, 5,400. And that is the diameter, right? That gets us all the way from here, all the way to there. So how about the radius? Well, the radius is half of the diameter, right? So 5,400 divided by 2 is 2,700. So drawing that in from the center to the edge of the circle, that is our radius of 2,700 right there. Okay. Now, can we find out the area of the circle? I think we can. So this is millimeters, of course. So 2.7 meters is what we want to work with. So pi times 2.7 squared, right? Times 2.7 squared. And it's the number that gets squared, right? Not the meters. That's why I usually don't write the meters in there just to not get confused. 22.902 meters squared, right? We just figured out the area of the circle. Okay, now can we find the area of the actual wall? Yes, we can. We can take the area of the octagon that we previously figured out minus the area of the circle that we just figured out. Area of the octagon, that's this guy right here, the 28.837. Meters squared, right? We're in area, minus 22.902 meters squared. 837 minus 22.902. Gets us 5.935. That is the area of the wall. Woo! That is quite a long trek, hey, to get there. Okay, now one more thing so we can actually find the volume of the wall. And that is our area times our height of wall. Right? We always have for volume length times width times height. Well, length times width, we already figured out the area, and now we just multiply by the height. So taking our 5.935 square meters times our height of 2,600 or 2.6. How many does that get us? 5.935, still have that in the calculator, times 2.6. Gets us 15.431 cubic meters. Woo! And that is the volume of the wall. My goodness. Okay, let's punch that in here too so we don't forget about it. 15.431 cubic meters. All right, cool. Let's move on to the next one then, shall we? Let's get my mark across, and we can get a little bit of volume of the footing in here as well. So that's the next question, volume of the footing in cubic meters. So we can see that the volume, the footing itself extends past the wall by 200 mils. So we'll have to take that into consideration. And it's not just a square, it actually is an octagon shape, right? So first, we need to find out the area of the big square. Because of course, we can turn this big one into a big square as well, right? So if I won't draw them all in maybe, but right, we can extend those as well and make a bigger square out of it. And that's the whole idea, that we're kind of doing that again of what we did before. So drawing this in for you over here, now the footing square in fully marked in and dashed lines for the wall. Well, we know that the measurement across was 5,900. That's a bit small, sorry. 5,900, right? That was our measurement of the smaller octagon wall square. And we know that it extends 200. So this is 200 right here. This is 200 right there. So all we're doing is adding that up. Right? So 5,900, oopsie, 5,900 plus 200 plus 200 should get us 6,300 for our square across. So that's from here to here, right? Or a big outside square. No, not it. This one. Big square, 6,300. There we go. Okay, so can we find out the area of that? I think we can. So 6.3 meters times 6.3 meters, right? 6,300. We can easily turn that into meters. 6.3 times 6.3 gets us 39.69 square meters for the area of the big square. Now we want to find the length of the side of the octagon, just like we did before. How do we do that again? Well, we figured out that the side is 2.414 times smaller than the distance across, right? So we can easily say 6.3 meters divided by our 2.414 gets us 2.6 meters. And we're going to take that as the length of our side of an octagon. So that would be this measurement right here. The side 2.610. That one right there. Okie dokie. Cool. Let's move on to the next one. Oopsie. Knocking things around here. Oh dear. Okay, here we go. Risky setup. Okay, here we go. Next, we want to find out our area that is not included, right? So we've done that before as well. So we just kind of want to do that again. We can do it the two ways, and I'll show you both again, just in case you need the reminder. Not included in the square, right? So those are the triangles. We can either draw ourselves that square again, divvy it up into 4 triangles, and we can say that the hypotenuse of these is the 2.610, which is the number that we just figured out for the length of our side of the octagon, right? So to find the area, we just say length times width. So 2.610, sorry, times 2.610, 2.61 times 2.61 gets us 6.812 meters squared. For the area of the triangles, if this does not sound like something that you enjoy doing, we can always do our SOHCAHTOA again, our trig, to figure it out. So I'll draw ourselves another triangle. We did already figure out that that the side length of our octagon is 2.61 meters. We know it's 45 degrees, and we want to find out the opposite side. All right, so I draw myself good old SOHCAHTOA triangle. What do we want to figure out? We want to figure out the opposite. Mark that up. So we're left with S times H. So opposite equals S times H. And then we can just fill in the blanks. Sine 45 degrees times 2.61 meters. Gets us the length of one side of the triangle, right? So 1.8455, let's call it. That is this one, 1.8455. Right, it's the same. Same as here. Those are the ones marked in red. Now, can we find the area of one triangle? That's what we want to do. Area, one triangle. We know that's base times height divided by 2, just like before. So 1.8455 times 1.8455. And of course, we're in meters, divided by 2. Gets us the area for one triangle of 1.703 square meters. And to find the area of all triangles, we just want to multiply by 4. Right? 1.703 times 4. Because we have 4 of them, right? 1, 2, 3, 4. Gets us 6.812 0.812. And looky here. That is the same as above. So before we were off by 0.001, and here we're deadly on. So it's a good way to do it. Now, we want to find, we're still on the hunt for the volume of the footing, but now we can actually find the area of the footing itself, right? So we can take the area, so area octagon footing is our area from the big space or big square minus area not included. Whether you did it this way or that way, it comes out to be the same, right? So the area of the octagon footing, we had figured it out on our previous sheet, was 39.69 square meters minus area not included, 6.812 square meters. And just punching that into the calculator. $32.878 square meters. Lovely. Okay, finally we have the area of the octagon. Now finally we can figure out the volume of octagon footing. So volume of the footing, just like before, we have the area of the footing, just figured it out, times the thickness. And that is given to us right here with the 300. So area, just figured it out, 32.878 square meters times 0.3, right? That's millimeters. We can't mix the two. Times 0.3 gives us 9.863 cubic meters. Okay. Fantastic. That is question number 2. 9.863 cubic meters. There we go. Awesome. You can see that the second time around, it really was the same as the first, but now you have a little bit more experience with it, so hopefully it wasn't quite so bad. All righty, let's move on to number 3 before we make this too long of a video. What is the capacity of the tank when completely full? Well, where is the tank? The tank is inside of the circle. So we already figured out the area, and I'll pull that back up. And then we really just multiply by the height, right? So number 3, capacity of tank when full, and it just says when full, right? In cubic meters, doesn't say it's full of anything in particular. So the volume of a cylinder is the area of the circle times the height. Okay. Area of the circle, we already figured that out, but just to show you again, is pi r squared. And we had figured out that r is 2.7. So pi times 2.7 squared. We can do it again. Pi times 2.7 squared. 22.902. And that was square meters because that was the area of the circle, right? We had already figured that out, but just to review. And all we need to do now is multiply by the height. 2.902 square meters, that's the area, times our height, that's the 2.6. $59.546 cubic meters. All right. So tuck this number aside because we're going to need it again for the following questions, and we'll pop it in here so we have it as well. So that was 59.546 546 cubic meters. And you can see that if you write everything out really nice and tidy and legible, and where you show what you're doing and what you're trying to figure out, not just writing out random numbers, if you have to restudy this for an exam or for your Red Seal exam and you haven't done it in a while, you can look in your notes and understand what you did. If you're just scribbling numbers, it's just a bunch of numbers. It makes it really, really hard. Okie dokie. Number 4. Okay, let's read this properly. When the tank is empty, assuming the standard density of concrete, that's something that should be in your books or that you can Google. What bearing capacity would be required of the soil to support the structure in kilopascals? This is where, carpenters don't necessarily need to know this, but it is a question and we're going to answer it. Nothing else, it's a good exercise in math and expanding our brains. So bearing capacity and with an empty tank in kilopascals. Okay, what we need to figure out here, first we're going to figure out the weight of the whole thing. And then we're going to figure out the force that it pushes down onto the soil with the help by gravity. And then we're going to figure out the pressure. So this here is kilonewtons, this is kilopascals, and the weight will be in tons. Okay, just so you know what we're going to be up against here. Yeah. Let's figure this out. So first, let's figure out the weight of the concrete structure. Because it's empty, right? In the next question, there'll be something on the inside, but here it's just the weight of the concrete structure. So we're going to take the volume of the wall plus the volume of the footing. And we're going to need to find out the weight, right? So these are in cubic meters, and the standard density of concrete is 2.4 tons. 4 tons per cubic meter. That's pretty standard. So to find that out, we'll just add times 2.4 tons per cubic meter. Okay, so now we're going to pop in the numbers. This gives us our volume in cubic meters, and here the weight per cubic meter, and we're going to end up with the weight at the end. So we can just take the numbers from here. So 15.431 cubic meters plus the footing 9.863 cubic meters times 2.4 tons per cubic meter. And you can see that they cancel each other out, right? If you imagine this is all on the top with the tons and this is underneath, kind of like the fractions are, we just end up with tons, and that's exactly what happens. So 25.294 for the two of these times 2.4 tons per cubic meter. And really, this is the step, because now we're multiplying it. This is the step where they would cancel each other out so that we get tons at the end. So we end up with 60. Now let's calculate it. So 15.431 plus 9.863, end up here with a 25.294. Oops, put it over there. Times our 2.4 gets us 60.706 tons. Okay, so we figured out the weight. Awesome. Now we need to figure out the force of the whole thing in kilonewtons. And the idea here is that we take the weight of what we just figured out of our concrete structure and we multiply it by the gravity constant of Earth. Could we use any gravity constant? Could we use the one of the moon or the Jupiter? We can't because they're all different. The more massive a planet is, the higher the gravity constant. So just for giggles on the side here, the moon gravity constant is 1.62 meters per second squared. Moon's pretty tiny, right? Jupiter, even though it's gaseous, but it's massive, 24.79 meters per second squared. So you can see that the force of the gravity is so much higher. And then something else that we need to know about this is that 1 Newton, and again, this is just for explaining where things come from. Not that you need to necessarily remember this. That 1 Newton is 1 kilogram times meters per second squared. And that, so 1 kilo, so the weight of something in kilos times what our gravity constant is, right? The measurements meters per second squared, that gets us a Newton. But we want to work in kilonewtons. So the nice thing is that 1 kilonewton is 1 ton times meters per second squared. And check this out, 1 ton, hey, we have tons right here. Woohoo! So we can use this, our weight times the gravity constant of the Earth, and we find our kilonewtons. So our weight is 60.706 tons times gravity constant of Earth is 9.807 meters per second squared. And when you multiply the tons times the meters in seconds squared, what comes out is kilonewtons. How cool is that? How? I'm not so sure. That's beyond me. But anyway, punching this into the calculator times 9.807 comes up with 595.34. And we are in kilonewtons. Cool. Getting closer. Kilonewtons is the force. We want to find out the pressure. So I'm just going to set this aside here so we can keep track. Next thing we need to find out is the kilopascals, which is the actual pressure. So that is our next step. Pressure on soil in kilopascal. Here's the rule again. 1 kilopascal is a kilonewton divided by square meters. So the force divided by the area on which it is pushing, basically. So what happens here is we take the force that we just figured out in kilonewtons and divide by the area of the footing. Bam. Okay, now we just need to punch in some numbers. So the force that we just figured out was the 595.34 kilonewtons divided by the area of our footing. And we just have to look into our notes. That was the 32.878 meters squared, right? You see kilonewton divided by meter squared. That's exactly what this is. Punching that into the calculator. 595.34 divided by 32.878 gets us 18.108 kilopascals. Wonderful. Engineers will be so happy. So we can pop that onto our sheet here, number 4, 18.108 kilopascals. Cool. Alrighty. Now, number 5, bearing capacity if the tank were full of water. So we still need to add all of this, and we need to add into the water. Let's check this out. So question number 5, we want to find bearing capacity. Tank full of water. That's important to know. And again, we are working with getting the weight, finding the force, figuring out the pressure. All right, that's what we're trying to get to our KPA at the end. Just so you know, water. Let's talk about water. 1 liter weighs 1 kilogram. Neat thing is that 1,000 liters fit into 1 cubic meter. 1,000 liters, therefore, is 1,000 kilos. That 1 cubic meter of water weighs. 1,000 kilos is 1 ton. That's the beauty of water and liters and kilos. Hallelujah. So now the volume of the tank in weight, that is actually fairly easy, which is exciting. So volume of tank in weight, right? We already figured out the cubic meters of it. And now we want to find out what it is in weight, in tons. So volume of our tank in cubic meters times the 1 ton that it weighs per cubic meter. Does that make sense? So we have our cubic meters, and we want to multiply, just like we did with the concrete before, by the amount in tons that it weighs per cubic meter. Beauty is that it's 1, so it really just stays the same. So the volume of our tank, so 59.546 cubic meters times 1 ton per cubic meter. This is the part where we can X out our cubic meters because we're multiplying them and they just cancel each other out. Punching it into the calculator. Do we really need to? I don't think we do. 59 times 1, it's just the same. 59.546, but tons, right? With that, we have figured out the weight. Now, for the next one, just like we did before with the concrete, we want to combine the mass or weight of the concrete that we figured out and of what fits inside. So the weight of the concrete, again, we figured out previously in where we talked about the bearing capacity empty tank. We figured out 60.706 tons for the concrete. So that's another number we need to continue working with. So we've got the 60.706 tons. That's the concrete, plus our water that we just figured out. 59.546 tons. And isn't that interesting? They almost weigh the same. 60.706 plus 59.546. It's 120.252 tons. Okay. So that is the total weight. Now we move into our force. And we remember from before, force in kilonewton is our weight times the Earth gravity constant. With how much, I don't want to say pressure, but how much weight and force is everything being pushed down onto the earth. So just punching in those numbers, 120.252 tons times 9.807 meters per second squared, right? That's our gravity constant. Should never change for Earth. 1179.311. Now we're in kilonewtons. Coolio. So that is the force. Figured it out. Super duper. Now let's figure out the pressure. And that is our pressure is our force divided by the area on which it pushes down. And that is the area of our footing, right? So we've got 1179.311 kilonewton divided by our area of the footing, 32.878. Gets us to 35.869 kilopascals. And that is the pressure. And that is what we're trying to find out with this question. Super. 35.869 kilopascals. Awesome. So we've done 1, 2, 3, 4, 5. Okay, 2 left. We got this. What's the next one? What bearing capacity would be required if the tank were full of steel? Okay, so we're doing the exact same thing once more, but the inside of the tank is full of steel, which has a different, let's call it density factor. Tank full of steel. There we go. And again, we are figuring out the weight. We're finding the force. Then figuring out the pressure. So steel weighs 8 tons per cubic meters. Holy moly, man, that is heavy. 8 times as much as water. 3 times sort of as much as concrete. That is wild. So we're literally doing the exact same thing that we have done twice now already. First, we want to find the weight of inside the tank. Right? So we've got our volume of tank, same number as before, times the density of steel. Punching numbers, volume of tank, that was question number 3. So 59.546 cubic meters times 8 tons per cubic meter. That's going to be very, very heavy. Let's punch that in. 59.546 times 8. 476.368. Wow, that is a whole different kind of number, isn't it? So with that, we have the weight of what's inside of the tank. Now we need to combine everything, right? So combine mass of steel and our concrete structure. So we take our weight, 476.368 tons, and then plus our 60 of the concrete, so 60.706 tons that we've had from before, because our concrete doesn't change, right? It just is. Now we're just filling the inside with different things. So adding those together, 537.074 tons makes. That is heavy. That is the added weight of the entire structure now, right? Concrete, and we filled it with steel. Now we need to get to the force. Earth's gravity. and we get our force in kilonewtons, right? In kilonewtons is from the weight times gravity constant. Cool. Now we just punch in those numbers. Same numbers before, 537.074 tons times gravity constant, 9.807 meters per second squared. So the number is still in the calculator, right? I'm not getting rid of that. Times 9.807. 5,267.085 kilonewtons. That is so many. Okay, cool. That means we have the force. Hooray. Let's figure out what the pressure is. And just as before, it's the force in kilonewtons divided by the area in square meters. So that's still the same area of our square footing that we're working with. So we're taking our kilonewton number, so 5,267.085 kilonewtons divided by the area, and that was 32.878 square meters. So again, I can just leave that in there. Divided by 32.878 gets us 160.201 kilopascals. And that gets us the pressure, and that gets us the answer to this question. 160.201 kilopascals. So depending on what we want to fill this thing with, has to be quite a bit stronger. Okay, now last question. We're almost there. Stay with me. Number 7, will it float? For that, we need to find out the volume of the entire structure, and not just of the of our concrete, but if you imagine it as a, let's see if this works, with a glass of water that you're putting in a bathtub, but it's empty, so I'm going to drink it. This is about displacement thinking. It's not about just weight of the concrete. So the concrete itself here would be my glass. But when you put your glass, next time you do dishes or you hop in the bathtub, try this out. You take a glass and you push it underwater, it displaces the entire volume's worth. Not just the volume of your glass structure, the glass itself, but also the volume of what's inside, even when it's air. That is the gist of this last question. If you can wrap your head around that, really go try it out. We're all hands-on people. Take an empty glass, push it into some water and feel the resistance. And then even see once you start tipping it and once you start getting water inside it, just how quickly it sinks. Okay, so we need the entire volume of what's on the outside, glass, here it's our concrete, and the volume that technically fits inside, even though it's air. So volume of entire structure. So we need to figure out, or just add, we already figured them out, the volume of the wall, the volume of the footing, and the volume of the interior tank. That gets us the volume of the structure. Okay, so let's punch in these numbers. We can just take them from here. So volume of the wall was 15.431 cubic meters. Volume of the footing, 9.863. Volume of the interior, 59.546. Well, let's punch them in together. 15.431 plus 9.863 plus 59.546. 84.84. So this is the volume that it will take up in the water, right? This is not the weight yet, but the volume that everything takes up together. So next step would be if the structure and the tank volume are in the water, how much would it weigh? I'll write this out. So structure, so that's our concrete, and our tank volume are in water. How much would it weigh? Because we want to find out if it would float, right? Would it weigh more or less than the water? So for the weight, we have the volume of our structure. We just figured that out right here. And we need to, we need to multiply it by the water density. Because we have a volume and we need to see if this volume would be more or less weight than what the water would weigh. Okay, so here we go. The volume of the structure, just figured that out, 84.84 cubic meters times our water density, 1 ton per cubic meter. Well, that just stays, we can scratch those out, and that just stays 84.84 tons. Right, so now that is the weight if all of this was in water, but it's not taking on water yet. Now, as a last step, we need to compare it to the weight of the concrete. So this is basically the weight of water that it would displace. And we need to now compare the weight of our structure because the weight is just the concrete, right? This is the volume because there's a silo and empty space on the inside, but the air doesn't weigh anything. So we now need to compare it to the weight of the concrete. Well, what was the weight of our concrete? It was 60.706. Oopsie, and that was tons. The weight of the structure is what we just figured out, right? 84.84 tons. So check this out. The concrete itself weighs 60 tons. But the weight of the structure, when we put it into water, all of this together, just like my glass of water, would actually weigh 84 tons, or that is the amount of water that it would displace. So the weight of just the concrete is less, right? Because our silo is not filled with anything. So if we stuck this whole thing in a giant bathtub, it would float until it started to tip where there were enough waves that it would start to take on water or the concrete would suck up water until it adds up so much that it would become more than this number. Then it would start to sink. Here we can say yes, which is crazy, right? 60 tons of concrete just floating in water. And the only way to remember it is that it's a glass, it's a sphere, and the volume that's on the inside that is also displacing water is empty. It's just full of air and it doesn't weigh anything, but it pushes and takes up space in the world. And that is why it would displaces a greater amount that would weigh more than just the concrete does. So there you go. that is one long worksheet. I hope that that was not as painful as it could be and that it was helpful. And yeah, good luck.